Hello, and welcome to the TI Precision Labs lecture discussing the different current loop transmitter configurations. In this video, we'll explain how 2, 3, and 4-wire 4 to 20 mA transmitters work, as well as compare applications and trade-offs between 2-wire and 3-wire 4 to 20 mA transmitters. In the previous lecture, we introduced 3 4 to 20 mA transmitter configurations, with the main difference between them being the number of wires used and how the transmitter is powered. The next few slides will go into further detail about the different configurations. A 2-wire 4 to 20 mA transmitter uses 2 wires to create a loop that transmits the signal current and supply to power the transmitter. The supply, transmitter, and receiver are all in series. In the loop, there is no ground wire. The transmitter can supply power to the sensor and its input circuitry, but these voltage levels all float with respect to the transmitter's return pin, iReturn. iReturn cannot be grounded to the loop supply ground or any other earth ground, but can act as a local ground to the sensor and its input circuitry as seen in the diagram. The transmitter, sensor, and input circuitry must also consume less than 4 mA of current for the system to be able to output the zero-scale 4 mA output level. These concepts will be explained further in a future video. A 3-wire 4 to 20 mA transmitter uses 2 transmission wires to connect the transmitter output to the load and the receiver's ground to the transmitter's ground. Typically, the third wire in this 3-wire current transmitter connects the local supply to the device, but there are applications where the transmitter uses the same supply as the receiver. The supply current and signal current are in 2 separate loops. This allows the transmitter to interface with inputs that need to be ground referenced. Because the output signal does not include the current consumed powering the sensor and transmitter, the output can go down to 0 mA. This allows the designer to use the common 0 to 20 mA or 0 to 24 output spans as well. A 4-wire 4 to 20 mA transmitter has separate paths for the supply current and signal current. Similar to the 3-wire transmitter, the 4-wire transmitter can use the common 0 to 20 mA or 0 to 24 mA output spans as well. The 4-wire receiver does not share a common return with the transmitter's power supply. This allows for several new isolation schemes, including fully isolated, power isolated, and output isolated transmitters, which can allow for the sensor, transmitter, and receiver to all be referenced to separate ground potentials. The next few slides will go over 2 examples of isolated 4-wire transmitters. This diagram shows a power isolated 4-wire transmitter. In a power isolated transmitter, the sensor and transmitter are isolated from the power supply. A common use for power isolation is when the transmitter supply is an AC power supply voltage that must be isolated and converted to a regulated DC voltage to power the sensor and transmitter. If needed in the design, the receiver supply and transmitter supply can be replaced with one shared supply. In this example, the input to the transmitter comes from a bridge sensor amplified by an INA 333. 4-wire configuration has an advantage over the traditional 2-wire transmitter because the sensor and input circuitry can consume more than 4 mA. This allows for high excitation current to low impedance bridges. The 2 signal current wires travel to the receiver and a sense resistor at the receiver translates the current signal into a differential voltage that's fed into an analog to digital converter. The next slide will show a fully isolated 4-wire transmitter, which is a combination of power isolation and output isolation. This diagram shows a fully isolated 4-wire transmitter. As seen in the last diagram, the power isolation provides the sensor and transmitter a common ground while being isolated from the power supply. Output isolation requires an isolation barrier between the sensor and transmitter output stage. In this configuration, a sensor is read through an on-chip analog to digital converter of an MCU. As you can see in the diagram, an ISO 7330 is used to digitally isolate the output of the MCU and the input to the digital to analog converter, which converts the digital signal to the analog VIN of the transmitter output stage. In this fully isolated design, the sensor, transmitter, and receiver are all referenced to different grounds. This can provide an advantage over a 3-wire transmitter that shares a ground over a long distance to the receiver if the environment is noisy. The rest of this video will focus on 2-wire and 3-wire transmitters. 4-wire transmitter design is similar to 3-wire transmitter design from the analog perspective. The 3-wire concepts brought up in this series can also be applied to 4-wire transmitters. The rest of this presentation will go over the differences between 2- and 3-wire transmitters and their applications. This slide displays the 2-wire and 3-wire transmitters side by side to help you see the difference in connections. You can see that the 3-wire transmitter has a local supply while the 2-wire transmitter is supplied by the current loop. Also take note that the iReturn pin of the 2-wire transmitter is not connected to the ground of the loop supply, though it can act as a ground to the sensor and input circuitry as long as the voltage is able to float. If iReturn is acting as a local ground, the current consumed by the transmitter, sensor, and input circuitry must be less than 4 mA. The 3-wire transmitter has a connection to the receiver's ground through the ground transmission wire. In the last lecture, we went through an application example using a 2-wire and 3-wire current transmitter to keep a remotely located liquid storage tank within a certain temperature range. In the next several slides, we will use this example to further highlight the use cases of 2-wire and 3-wire transmitters. 2-wire transmitters are good for use with sensors placed remotely in the field that have no access to a local supply. V-loop can supply the transmitter and sensor. In our example, the liquid's temperature must be measured below the surface, meaning a submersible temperature sensor is required. The possibility of providing an onboard power supply to power the sensor is limited. Due to the remote location, supply availability, and type of data to be transmitted, the 2-wire approach was chosen. The 2-wire transmitter receives an input from the temperature sensor, which is translated to the 4 to 20 mA signal in the transmitter. 2 wires are used to connect the remotely located transmitter to the central monitoring station. Those 2 wires provide power for the transmitter and sensor and carry the return signal containing the proportional current based on the sensor's reading. The current is converted to a voltage when it passes through a resistor, and the resulting voltage is then read by the monitoring station. 3-wire transmitters are good for sending control signals from the monitoring station to a control element where the transmitter is able to be powered by a local supply. 3-wire transmitters are also used when sensors use input circuitry that require current greater than 4 mA, such as an input from a microcontroller. Looking back at our example, commands were sent to a valve to let heated water into the tank if the temperature of the liquid became too low. The valve does not require power to be sent from the monitoring station because it has its own local power supply. Because the transmitter will be located near the monitoring station where there is a power supply, a 3-wire transmitter should be used. The 3-wire transmitter receives an input from the monitoring station where it's translated to the 4 to 20 mA signal in the transmitter. The transmission to the valve consists of the current signal and a ground reference to tie the valve's local ground to the transmitter's ground. Next, we will discuss the trade-offs of using a 3-wire versus 2-wire solution. There are a few trade-offs when choosing a 4 to 20 mA transmitter. First is the cost. 2-wire transmitters tend to be lower cost. A 3-wire transmitter requires a third cable and, if powered locally, requires an extra supply versus the loop-supplied 2-wire transmitter. The next trade-off comes from the design side. When designing the transmitter, there are some extra considerations you need to take for a 2-wire transmitter. The 2-wire transmitter, sensor, and its input circuitry need to consume less than 4 mA of current. You cannot connect the iReturn pin to V-loop ground. This could be a problem for sensors or inputs that need to be referenced to ground. This also leads into the next trade-off. You cannot connect multiple 2-wire transmitters to sensors or digital to analog converters with multiple outputs without adding isolation. This is because the iReturn pin of multiple 2-wire transmitters cannot be connected together. We'll show a visual of this on the next slide. Here we have an example of multiple 2-wire transmitters sharing the same V-loop supply. The XTR116, a 2-wire transmitter, has an onboard voltage regulator and voltage reference. If all sensors and their input circuitry have separate ground pins from each other, they can all be powered by the individual voltage regulators on the XTR116s, and the XTR116s can all be powered by one loop supply. If the transmitters have inputs that come from one sensor that has multiple outputs, or a multi-channel digital to analog converter, there will be conflicts between the iReturn pins of the 2-wire transmitters. Remember, the iReturn pins of each transmitter need to float in order to provide the correct 4 to 20 mA output current level. In this example, one XTR116 is providing the reference and supply voltage to the digital to analog converter. If the digital to analog converter was trying to output values corresponding to 4 milliamps, 10 milliamps, and 20 milliamp output currents out of each channel, the iReturn pins of each transmitter should float at about 1.1 volts, 2.75 volts, and 5.5 volts respectively. We will go through how those values were derived in a future video. With the iReturn pins tied together to the ground pin of one of the multi-channel digital to analog converters, as seen in the diagram, the iReturn pins will not be able to float independently to provide the correct current output. The alternative solutions would be to use 3-wire transmitters, which are ground reference, or add isolation to the input of each 2-wire transmitter. This isolation scheme will be introduced in a future video. As mentioned in the last example, 3-wire transmitters could be used as an alternative method to connect multiple transmitters to one digital to analog converter with multiple output channels, as shown in this diagram. Because the 3-wire transmitters are ground reference, there is no problem with connecting the outputs of the multi-channel digital to analog converter to the inputs of the different transmitters without input isolation. That concludes our video comparing 2, 3, and 4-wire current loop transmitters. In the next video, we will dive deeper into 2-wire transmitter topics. Please try the quiz to check your understanding of this video's content.